Hello everyone. How are you all? Welcome back to this channel and welcome back to this video. So this in this video, uh, I'm going to share my thoughts that I have had and the things that I have believed in terms of what is the future of AGI. So I believe that gaming and artificial environments and uh, reinforcement learning in general is the future of training AGI. Uh, I also have published many materials regarding the same, uh, advocating for uh, better for the construction of better techniques, right? Reinforcement learning techniques for to include reinforcement learning in the training phase. So this video, I'm going to give you the reasons why I believe that, and also we are also going to do like a case study on that on one large language model that has been using reinforcement learning. You might have been aware of that, which is Deepseek, right? I've already made a video on Deepseek, which is basically like a live paper walkthrough, so not like uh, me providing you content. But anyway, hello and welcome to this video. So let's get started. Um, right. How do I? Okay. So before watching this video, there is some recommended content that I mean, okay, maybe I recommend you to maybe watch those videos before coming to this one, which is the two videos that I've uploaded previously on multi-agent cooperation for building moral traits or building responsible AI. Right? On building responsible AI, I've made like two videos, which is like maybe recommended uh, for you to watch before watching this. I mean, just recommended. It's not mandatory. It's not like a prerequisite, right? So let's get started, right? Um, let's get started. So the first we are going to go through this paper, which we have already went in the last video, in one of my last video, which is like a reading, live reading. So maybe not very recommended. I don't recommend you to watch that video. So I've highlighted the main points. Again, DeepSeek is a model that is like on a very high level. DeepSeek is a model that utilizes uh, that does not necessarily rely on like supervised fine tuning. You can see this point here. So um, so basically, don't get me wrong, but I think until now the like the super like the insane performance of large language models, right? I mean, LLMs have been performing at like next level, right? Like if you have insane intellect, like cognitive prowess, right? These LLMs are having like insane cognitive prowess. Like they are able to like now scroll through the internet, like and just go through like very large documents and provide us summaries, understand things, and answer questions within certain contexts, right? We have very powerful LLMs right now, but I believe and I think that the power of LLMs can only be attributed to the vastness of the data we have, right? Right, the vastness of the internet data we have, and number two, the computational prowess that we are able to that we have access to, right? So no, not we, right, but corporates. So the computational prowess, like the computation and the data, is probably the only reasons why these models are performing very well, right? And on a deeper level, right, what these models are doing is they're just predicting the next word, right? So fundamentally, the objective of these models, these large language models, is basically to produce or generate the next word, which is which is probably most relevant, right? So what the model does is it goes to a lot of data on the internet that it finds, which is human generated data, and so basically its goal, right, after training. So in training, it has to like predict the same word, but after training, so what it basically does is it tries to sound more like a human, right? That is its primary objective. And so basically, so therefore, consequently, and inevitably, engineering problems and science problems, science related problems, right? We have many science related tasks, and sequentially done tasks. Like some tasks need to be like done in certain sequences, and many reasoning related tasks and mathematical problems, right? Many problems related to mathematics and many other engineering problems, for example. Well, these problems, and so definitely these models cannot solve these problems because the model's main objective is to sound more like a human, right? Is to replicate the most of the data that it has already seen. And so basically it cannot like generalize easily to a more different questions, right? And second of all, well, that is a point. With so these models are just not suited for reasoning type of task, for like actual problem solving, right? So basically, that is the reason I think these models are actually not, I mean, they are just not performing well on other tasks because all they so because their objective basically is to sound more like a human, right? So that's why it is maybe better, right, to use reinforcement learning, where in reinforcement learning it's about solving problem, right? It's like a game, and not like a game, but it's like you put your agent inside an environment, and the agent has like find the correct policy to go through the environment and come up with the most well, come up with the highest reward possible, right? So that is the best way of probably portraying this problem of language modeling, right? Or AI agent, or AI training, right? So it should be the objective of AI to solve a problem and not take the next word. So in games, right? In games, you can see this trend where even in chess, right? In chess, we have uh, temporary sacrifices. Like we make temporary sacrifices to achieve so to increase the total reward. So in order to get a checkmate, for example, to win the game, we have to sacrifice some pieces, maybe, like, and also give up some positional advantage, right? So we do all this temporary stuff to actually win the game, to solve the problem. And that is with reinforcement learning, right? It's not about predicting the next word, and it's not about sounding more human with the next word, but it's about solving a problem, right? It's about increasing the total reward, which may be like making it more understandable, right? Making the text more coherent. Maybe that could be the final objective of the model, or maybe solving a problem, right? Coming up with reasonable steps to solve a problem, and also with reinforcement learning, we have this the model, like, fundamentally reinforcement learning, when there's like a path where a model figures out a path to go from the question to an answer. It like it also has this experimentation, right? This experimentation capacity. Like the reinforcement learning algorithms, they also have, I think, certain type of algorithm encoded in their uh, mathematical framework, so that they actually try out different steps, right? So they try out different steps, and also they see if there is a better way to get to the answer, maybe maybe more efficient way. So that is also very important, because in real life, in the real life world, uh, we have like, there is no one way of getting a solution, right? There is always going to be a better way, and experimentation is always a very good strategy in terms of problem solving, right? So that is also uh, i think I think is promoted with reinforcement learning based algorithms, right? And also multi-agent reinforcement learning. I have been a huge advocate, because I believe that it is only through societal interactions that uh, true individuality of an agent is developed, and we want that, because it's only through development of empathy. So it's only through a development of individuality, and the it's only through development of this ability to stand or take the shoes of your neighbors, right? uh, which is, I mean, there is I made like a whole two videos on that, so check that out if you're interested. So that it's only through social interactions that we could uh, that a model could truly develop empathy, which might be, I mean, which could be a huge stepping stone. Who knows the number of problems that we could be able to solve once we could make this model truly conscious, in the sense that in the sense that they could actually uh, replicate or imitate some human human level emotions, right? So or yeah, empathy is emotion, right? So it's understanding of your, I mean, it's the ability to uh so what is consciousness, right? So consciousness is like like being aware of any environment and try to figure out things on your own, right? You don't have a cold start in all, in all of all of the real world. So this development of individuality might be a, you know starting step for the creation of consciousness. Okay, anyway, so multi-agent reinforcement learning systems, right? Multi-agent reinforcement learning systems are agents. So we have multiple agents, right, which whose objectives might all be like unified. So they all these agents might actually be working for a unified objective, or each agent might have its own objective, and these agents might negotiate with themselves, which is actually crazy idea. It will be very great if this happens, right? So these agents to actually like negotiate with each other. Well, I mean, that's what I mean we could be able to like mimic the human way of how we developed maybe a lot of our conscious uh, maybe a lot of our consciousness, how we develop our, it's how we develop all of our consciousness, maybe these interactions with each other and negotiations with each other, like I'll help you, help me with that. So like that sort of stuff. So yeah, we can have like different types of multi-agent reinforcement systems, which could eventually like make a great training paradigm for these large language models, right? So that is what we believe, right? This, like, we have a lot of papers. I mean, I couldn't cover them all in this video. I can't cover them all in this video, not only because I haven't read them, because I didn't have the time to, but also because I don't want this video to be very lengthy, right? We have these papers on LLM based multi-agent reinforcement learning. So this paper is more like uh, it's not how multi-agent systems can improve LLM training. It's about how LLM LLMs, right? So how language can positively influence multi-agent reinforcement learning systems. So that is what this paper is about. This paper is about, and also I think we have an application. I haven't read this paper, and I'm not even aware of its uh, theme, but might be a cool paper. We'll get to this paper in the future if we can. Right? We have also some papers. I'll link these papers in the description. So if you are interested, you could actually go study them. And I'm also working on one like article of my own. I'll call this an article. But yeah, I mean, so we have some like I haven't like completed this paper or anything, but it could be. I mean, maybe I'll try finishing this paper, right? So it's also based on using multi-agent reinforcement learning systems for development of consciousness. Anyway, so this paper will go through first R1 on a very high level. Okay, so the main contributions from of this DeepSeek, right? We'll go in a very high level. So is they do not necessarily rely on SFT, supervised fine tuning. So basically, we have a pre-trained model which will train on large human data. Again, this is the same objective of predicting the next word, right? And then after that, we can fine tune the model for a specific problem with a specifically customized data set for a specific problem. But then we do not do this supervised fine tuning. So what we do is, um, so this okay. So we'll use chain of thought. So say chain of thought is a system, or is a set of technique. So chain of thought is a technique to improve reasoning inside model. So the model actually comes up with reasons, right? Comes up with reasoning steps, and not only just like uh, and not only like just generate the word to sound more human, which is the general objective of any LLM until now. Uh, right. So DeepSeek also like demonstrates like self-verification and reflection. We'll get to that in just a minute, which is also very interesting. And also they have this paper, the DeepSeek paper. They have also introduced distillation to be very powerful too. So what we do is We have let's say we have a very powerful model, right? So so what we do is we give in some prompts to this model, and we'll get the output from this very powerful model. And based on the inputs and outputs of this model, we'll actually train a smaller model, which can actually like generate the same data. So the same output that its parent model, which is a powerful model, can generate, right? So, and also the thing is, we'll ask the parent model, the powerful model, to generate the reasoning steps, right? So it has to like it does not just like give us the answer, as in sense just giving the answer, but it also uh, generates the reasoning that it had done to get to that answer, right? So, and we also want the student model to replicate this reasoning, right? These reasoning steps, which is very nice, and it does uh, give us some very nice results. Like this is like that's stated in this paper, right? uh, so in this section of the paper, we can explore that uh, the we can explore the potential of LLMs to develop reasoning capability without any supervised data, right? Through just self evolution through a pure reinforcement learning process. That is what Deepseek R10 is based upon. Like there is no supervised fine tuning phase, right? There is only a reinforcement learning through a pure reinforcement learning phase. We optimize the model, right? So this is the objective the model has to optimize for. So we use something called group relative policy optimization. I have covered this in the last video in the DeepSeek paper, but anyway, I'll go through this in a very high level. So what we are basically doing, what is he here anyway? So what we are doing here is basically we are going to this is the so pi is a policy, right? So pi is a policy. So it is going to generate like a probability on how likely, or it's like, yeah, like it rates each answer. So for each word, it's going like rate the word on how relevant that word is to put in. So or how relevant a response is, right? Maybe to be more precise. So we're going to get I think, yeah, so we have to get the relevancy, or policy, or reward, right? I think that is reward. Yeah. Yeah. So we are going to get the reward for certain output, and we're going to divide that by the reward given by the old policy, right? We're going to update this policy. So we're going to start off with an arbitrary policy and then update this policy as we go on in the training loop. So, and then we're going to get the minimum value. So we also have this advantage magnet. So this measure. So we have this quantity called advantage, which is basically this equation, which is, so for each response, we're going to get a reward, right? And we're going to subtract that reward with the mean of all the responses. So mean reward of all the responses, right? And then we're going to divide that by the standard deviation of the responses. So basically, higher advantage for a response means that mean of the of all the responses is relatively lower to the reward of a specific response, of the corresponding response, and the standard deviation is as low as possible, right? Only then we can have higher advantage for a certain uh, response, right? So that is right, so that is advantage. And so that is what we're doing here, right? So we're also clipping this value between a certain range, 1 minus epsilon to 1 plus epsilon, right? And we're also having a KR divergence term to make sure the model does not diverge too much from its older policy. So we don't want the policy updates to be too large for stability purposes, to increase stability, right? So that is the optimization objective. So pure reinforcement learning objective. We don't have a supervised fine tuning phase. But you may ask, how about the rewards? How are these rewards calculated actually? But so what happens here is, uh, so these rewards are actually objectively determined, right? So the type of problems we are solving here, for the the type of problems for which this model is applied, is going to be like objectively determined problems, which are like mathematical problems for which for a question there is only one answer, right? So and also for programming related problems, we're going to have certain test cases, for example. So the reward is going to be uh, like if you pass if your code pass the test case or not, so that is going to be the reward. So right, so these are objectively determined, so we don't have to actually train another model. So in RLHF, right, in general reinforcement learning alignment techniques, we have to like train a reward model, right, which is actually which is actually supervised fine tuning. So it is it learns, right? So it's basically a discrete it's a ranking model. It provides a certain reward for a response, right? So what we do is we collect a lot of question answer pairs, right, or query response pairs from humans, and these humans will actually rate different answers, right? And we are going to so these ratings we are going to train a model on this rating data. And after training a separate model after training a separate reward model, the objective of the LLM would be to generate responses in which would be to generate responses for which the reward model gives a higher reward, right? That is going to be that is the original RLHF workflow. That's how original RLHF works. But in this deepseek study, in this case study, so in this case actually, so deepseek, we are only solving objectively determined problems for which we don't have to train a reward model, right? So the rewards are specified, right? There is only one answer, and these answer actually we have many data sets that have many mathematical problems and coding problems and physics problems, who knows, maybe chemistry problems. So we have many of these objectively determined problems, right? uh, Specified problems which have only one answer, right? We don't have to train a model to determine the reward in each case. So yeah, that is how we'll fine tune the model, right? uh, and while fine tuning, we have this objective will be, so the model will try to maximize this objective, right? uh, so that is a reward model. Okay. Yeah, not only accuracy, in accuracy problems, we have a previously like I have told you, a specified reward model we don't have to train another reward model, because the answers are specified already, right? Because there are mathematical problems and coding problems, software problems. And another type of reward is actually format reward, which is actually very interesting. So in the model's response, if the model uses tags such as think tags, or we have many tags, right? Thought tags. So to denote the model's thinking process. So the model, while the model is thinking, it is also asked to the generate what its thoughts are, like what is the reasoning that it has made to come to the answer, right? So based on this, we also apply the reward, so assign the reward. So if the model comes up with good formatting with good reasoning steps to come with the answer, the model will be given higher rewards. Again, we don't have to train another reward model. It can be specified already uh, with some hard coded algorithms, right? So again, that is a power of DeepSeek, right? We are not supervised fine tuning, right? Anywhere. um, Again, the self-evaluation process of DeepSeek R10 is fascinating demonstration of how RL can drive a model to improve its estimation capability. By initiating RL directly from the base model, we can closely monitor the model performance without influence of. Okay, I mean, you could read all that if you are interested. Again, one more interesting observation that the researchers have made is that the model actually can self-reflect now. So it has something called an aha moment, right? So it basically like, so while reasoning in its reasoning uh, process. At a certain stage, it can actually revert back, right, and look back upon its decision, and maybe come up with newer decisions, right? So that is the advantage, and that is why I believe that gaming is the future of AI training, because in such situations, there is always going to be efficient way of dealing with problems, right? So this is basically problem solving, right? This is unlike the LLM, or like the standard transformer, or LLM training, in where uh, generating the next word is the problem, right? It's very uh, simple, right? It's just not complex enough. Like, it does not, like this the objective of generating the next word and sounding more human just does not get the uh, point, right? It just does not get the point. We want AI to be problem solvers, and actually find better ways, or find efficient ways to actually solve a problem. So that is why I think reinforcement learning is the way to go about training future AI models, or coming to AGI, or reaching AGI. So so you can see one example here. So while the model is primarily solving a problem, it can actually have this aha moment. You can say that I had a better way to solve this problem, and can actually start the problem from this beginning, which is very very interesting, very very good uh, improvement, I would say. I mean, yeah. But there is a drawback of Deepseek Carbon Zero, which is poor readability, and it also like mixes languages. Again, that makes sense. That does make sense, because in a reinforcement learning setting, the goal of the model is to come up with the answer. Right? The goal of the model is to increase the final reward, and the reward in the Deepseek Carbon Zero case is actually coming up with the right answer, right? In the sense of generating good format, right? Generating good reasoning steps, that is a reward. And number two, uh, coming up, in terms, in the case of specified problems such as coding problems and mathematical problems, its goal is to actually generate the answer, right? Readability is not encoded in its in its objective function, so therefore it is expected, right? However, in the deep sea carbon scenario, we have something called a cold start phase. So um, so it's basically like we do use supervised fine tuning. So we just do it on some COT data, on chain of thought data. And also we have another. So in order to uh, restrict the model or constrain the model from stop the model from mixing languages. So we add another term to the objective function, which is basically I think, yeah, I remember it. So the proportion of words of a certain language in the prompt, right? So in the prompt we have some proportion of words in a specific language. For example, we have 94% of English words in the prompt. Then we also want the proportion. We want the proportion of the words in certain language in the prompt to be equal to the proportion of that specific language uh, in the response, right? So that is what we so we'll do that to make sure that the model does not mix languages, right? Like, if there is more number of English words, the model should predict. So in the response, more English words should be present, right, to prevent language mixing, right? That is what we do. So that is, we can see here, yeah, proportion of words should be equal in both the responses. Like, yeah, you get that, right? uh, Again, for some scenarios, right, for some scenarios, this format reward and accuracy reward might not be very relevant, right? So in many scenarios, in fact, we like that will not be relevant. Sorry for that. For some scenarios, accuracy rewards and format rewards might not be very relevant, because we'll have more general data, and determining accuracy might actually be a problem. So in that case, we will use we will use uh, a different model. We'll train another model on capturing human preferences, right? Again, that is reinforcement learning. mm, and distillation also, right? uh, yeah, so these people, for the Deepseek model, for the decision models, they only applied SFT and did not include the RL stage, right? I don't know why. uh, I mean, you have all these results. I mean, I don't. Yeah. So please, if you're interested, you can go through this result, and I'll post the link of this paper in the description. So make sure to check that out if you're interested too. Now, let's get to the architecture, right? Let's get to the architectural. So this is like this part of this video is more like a bonus. It may like divert from the uh, heart of this video, which is the reinforcement learning, right? So we are going to like look at some changes that they have done for their in their architecture in this video. So let's see what they've done. So the first thing that they have done is replace the uh, standard attention block with a multi-head latent attention, which is called MLA. So what they've done basically is that, we can actually see this trend in some research, in some latest research works, like related to maximizing computational efficiency in developing in training models. So we can also see this in next flash attention, I think. So where uh, computation is seen as computation is seen more um, carryable, right? So computation is actually easier to do in this age rather than storing it in memory. So I think we do something so what we do in flash registration is I don't remember the details, but what